So you may want to, well, I'm not going to make that video soon. Maybe I am, okay? But anyway, let's go through this specimen paper first, okay? So you may want to check this out why this is, okay, that means not unique solution, okay? Part B determines the value for the system to be consistent. Consistent means have solution. Have solution. Okay? Well, for a system to have solution, there are two ways to have solution. One way is you have unique solution. Second way is you have infinitely many solutions. Okay? But in part A, we have already shown that there won't be any unique solution. So the only way to have solutions to be consistent is you have infinitely many. Okay? How do you have infinitely many solutions, right? The answer is you need this to be 0. Okay? Yeah, that would take me the other video. Yeah. But the reason is the last row would really mean 0x plus 0y plus 0z equal to lambda minus 3. So this is all 0, right? So how could 0 be equal to some number? Well, the chance is only when this is 0. Okay? So unless you have this, there won't be any solution. Okay? Therefore, you really need the last slot to be 0. Therefore, you need lambda minus 3 to be 0. That means lambda is 3. So done. I've determined the value. For this value, find a general solution of the system. Okay. So how do we find the general solution, right? So lambda is now 3, so never mind. If we look at this, we would have here y minus z equal to 1. So what we do is, originally there were 3 equations. After making lambda 3, this is 0, 0, 0, 0. So it's basically useless. So it's kind of like we're solving 2 equations with 3 unknowns. So the idea is that the equation would have infinitely many solutions because one of the unknown could really be anything it like. After that unknown determines its value, the other 2 would become 2 equations, 2 unknowns, and could be solved uniquely. But the fact that one of them could be anything at all means there are infinitely many solutions. So this is the idea of how do you write down a general solution. We allow one of the variable could be anything it like. So we usually take that to be z. So we let z be just some number, t. Okay, t is a real number. Whatever it is, okay, so we just allow z to be anything. Then we solve for y in terms of that. So t, this is y. And then look at this first one is 1x plus 1y plus 1z equal to 1. But y is 1 plus t. Z is t. Z is t. Therefore, x simply equal to minus 2t. Okay, and therefore, we usually write in a vector form, x, y, z would be negative 2t, 1 plus t, and t, where t could be anything. So this is a general solution. Whatever solution that fit this system, after we take lambda to be 3, would kind of be like this form. Okay, and you can see that infinitely many because t could be anything. And if you're good at vector, you will be able to see that this is actually an equation of a straight line. So all of the solution would fit to be a straight line in the 3D, three-dimensional space. Okay, so you can see the system equation is highly linked with vector equation and matrix, and it's kind of mystical why IB would take away matrix from its syllabus. But never mind, it's done. I'm pretty sure after a few years it would be put back to the syllabus. But meanwhile, we're going to stick to this method, the row reduction. Okay. Oh, time is clicking. Now we move on to a long question, a structured question. And this is the surprise. The syllabus says an informal idea of continuity of function. Well, this is not informal. This question is highly standard. Okay, it's like everything you can know about continuous for a high school level. Okay, unless you're say major in math, I don't think anyone would know more about this, about continuity. Okay, and that's pretty formal. All right. So anyway, I gotta admit to my students that I didn't taught you this before because I don't know this is gonna show up. So I hope this video could help a bit. Okay, it states that the function f and its derivative f prime. The derivative can also be treated as a function, so it's still a function. It's just a derivative function. Both of the functions are continuous for all values. Okay, just for this, they ask you to find AB. Oh, come on. What do continuity means, right? So I'm gonna tell you this now. For a function f(x) to be continuous, okay, at any value, say a, at x equal to a, what we need is so what is the meaning of continuous, right? If you look at the graph, we take the value a, we need a. Since this is a function, it will have a functional value of a, so it's like fa is here, let's say. This is fa. What is the meaning that the function is continuous? That is, if you go to the left-hand side of the function and walk along the function, when you go to x being a, you should really go to this point. That's the meaning of continuous. So I don't care how you walk before, but when x is a, you should come to this point. Okay, so this is continuous. So being continuous means you have the functional value fa, and you can travel along the curve on the left-hand side. So in math, we write that as limit x go to a fx, and I want them to be the same. I want them to connect at this point. That's being continuous. But just seeing this is not enough, because what about the other side? Okay, what about after this point, the graph just go to there? Then it's still not continuous. So I also need the other side to join together. Okay, so the other side is written like this. I need another limit. Okay, and I take the right hand limit and left hand limit. Negative means I go from the negative direction, while positive means I go from the positive direction. So you need these three things to be the same at that point for the function to be continuous at that point. And for f and f prime to be continuous for all value, that means no matter what this a is, for every value a, this is true. That's the formal definition of continuous. This is the most formal that you can get. Okay, except maybe you do not know the rigorous limit notation. Other than that, this is the formal definition of continuous. Okay, so I'll be triggered a little bit, I would say. And well, let's do the question now. So part A, given that f and f prime are continuous for all value, find a and b, find a and b. So what is fx? Let me copy fx. If it's 2x minus 1, x squared plus bx minus 5 for the range x smaller than 2 to smaller than x smaller than 3. Now, if you look at the function itself, when x is before 2, this is a piecewise function, right? When x is before 2, this is just a straight line. When x is between 2 to 3, this is just a parabola, quadratic parabola. So for each of the pieces, they would definitely be continuous because they are just either a straight line or parabola. Both of them are continuous. So the only problem seems to be when x equal to 2. That is, when you change from this straight line to this parabola, would the graph be broken? Would the graph be broken, right? So would it be like this, straight line, and then parabola? Okay, oh, they do not connect, okay? Then it is not continuous. So that seems to be the only change, the only problem that we need to consider, okay? Since they also talk about the derivative, we may just also find the derivative. So we differentiate this 2, differentiate this as 2ax plus b. For x to be 2, x to be 2 to 3. Then they says both of them are continuous, so we're gonna use this. For the fx, since for the left-hand side, for the left-hand limit, x is smaller. When x is smaller than or equal to 2, we'll just do this. Okay? That means when x is smaller than 2, we do this. When x is equal to 2, we also do this. So these 2 part would really be would really agree, because for the left hand side they follow the same thing. So the only problem is the right hand side, right? So to 2 on the left, okay, fx, I need it to be the same as x go to 2 on the right hand side, fx. When you're on the left hand side, you use this one. So it's 2 times 2 minus 1. Okay, we just plug 2 in. That's usually how we calculate limit, because you don't know the correct way anyway. For this one, we just plug 2 into here. A2 squared plus 2b minus 5. Okay, so what is this? This is 3. So this implies that 4a plus 2b minus 5 equal to 3. Okay, that's for the original function. What about the derivative, right? For the left hand limit, I need it to be the same as the right hand limit. The left hand limit is just 2. Right hand limit is this. 2a times 2 plus b. So what I have is 4a plus b equal to 2. Okay. What's next? So we move it to there is 8. We subtract. Right, 8 minus 2 is 6. 2b minus b is b, and a is gone. Therefore, we got that b is 6. After we got b is 6, this is 6. 2 minus 6 is -4. Divide a is -1. So in this way, we found a, b. Okay. And then so a is -1, b is 6. Then for the other two parts, it's even harder. Really. Okay, first, show that f is 1 to 1. How do we show that? Okay, if you do option, if you do set relation and group for your option, you would have learned this. But if you do that way, due to the fact that this is a piecewise function, it's pretty tough. Okay, so the normal way is we let fx equal to fb, then we want to show that a equal to b. But this is really not in the syllabus if you're just doing core and not doing the set and relation option. So what happened is, for this time, we have got the derivative, right? And the derivative is 2 for x smaller than 2. And since a is -1, so it's -2x, okay, plus 6, b is 6, right? And since x is between 2 to 3, so this derivative must take value. Okay, so x is between 2 to 3, right? So -2x plus 6 must be between 0 to 2. Okay. Now what does that mean? It can never be actually 0. That means this is always positive, and this is also always positive. And if you have good knowledge about derivative, the gradient being positive means the function is increasing. And if the derivative is always positive, that means the function is always increasing. So it can only increase. It cannot go backward. All right, it cannot go down. Okay, sorry, you can see. It cannot go down. It's always increasing. What does that mean? That already means the function is 1 to 1. Okay, because how can you be not 1 to 1, right? You have to go down a bit. Then this is not 1 to 1, because 3 different values of x give you the same y. Okay, then the function wouldn't be 1 to 1. Okay, yeah, we call this many to 1. So 3 different x map to the same y. But if the function is always increasing, okay, you will be 1 to 1. So that's why. That's for part B. Okay, I will argue that's already pretty tough. Okay, lastly, obtain an expression for the inverse function and state the domain of the inverse function. Okay? So, well, I just show you once how you do this, right? We have the function. Since the function is piecewise, the inverse will also be piecewise. Okay? So let's do this part first. Okay? For the first part, let y equal to, oh, I'm running out of ink. Let's do the other side. y equal to 2x minus 1. We swap x and y and then make y the subject. Okay, easy, right? For the expression itself. But we also need domain. Okay, the domain of the inverse, if you're good at this, okay, so this is the function, this is the inverse, right? We call this the domain, we call this the range of the original function, okay, of the original function, okay? But what about the inverse, right? For the inverse go backward. Therefore, this is really the domain of the inverse, and this is the range of the inverse. What does this tell you? Therefore, the domain of the inverse is really just the range of the original function, So we can obtain the domain of the inverse like this, if you understand this diagram. Okay? The domain of the inverse is just the range of the original function. So if you look at the original function, okay, for this part, what is the range for this part? Okay? Since for this x is smaller than 2, okay, so x is smaller than 2, yeah, x is smaller than 2, so 2x minus 1. 2x minus 1 will be smaller than 2 times 2 minus 1, smaller than 3. Okay, therefore, the range of this function would be smaller than 3, the range of the original function. Therefore, the domain for the inverse, would be x is smaller than 3. Okay. What about the other piece, right? So we're going to need the values, negative x squared plus 6x minus 5 equal to y. We swap x and y. And then we need to make y the subject. How do you make y the subject, right? We usually do something called completing the square. Okay? So, well, let's say all of you know how to do completing the square. So I'm going to do it quick. So this is how I do the completing the square. You can try to do it off the video, okay, slowly, and see if you can get something similar. And then we move the 4 to the other side. Take away the negative. Take away the square. So y minus 3 equal to plus or minus square root x. Okay, so we take the square root, and then what? Okay, so it's like this. Okay, since we know that the domain of the original function is between 2 to 3, okay, therefore the range of the inverse, okay, must also be between 2 to 3. Therefore, this guy must be between 2 to 3. Therefore, which one should we take? The positive one or the negative one, right? It needs to be smaller than 3. Therefore, obviously, we take the negative one. Therefore, the inverse for this bit would be y equal to 3 minus 4 minus x. Okay? And then we need to see, okay, when would this thing really be going into the range of 2 to 3? Okay, so when is it 3, right? When this becomes 0. When this becomes 0. And when x is 4, this is 0. Therefore, x seems to be able to take value at 4. 4 is okay. And when would this be 2? 3 minus 1 is 2. So we need this to be 1. Okay, and it seems that root 1 is 1. So when x is 3, this would be 1. So it seems that x would take value between 3 to 4, okay, for the domain. Therefore, the domain is x between 3 to 4. Okay, so you can do this way or you can do this way, okay, thinking about, okay, the domain of the inverse must be the range of the original function. So both ways works. You can try both ways. And this is basically the answer. So you write down the answer here. So inverse There are two parts. The first part is this. Second part is this. This is when x is smaller than 3. The other one is when x is between 3 to 4. And that's it. And I have to admit, this is one of the hardest questions in the whole Speicemen's paper, especially because it's almost out of the syllabus. I can't really say it is because, well, it's released from the IB. Okay, so it's technically officially always inside the syllabus. But other than that, I would really say they cheat a bit, because this is not an informal way of doing continuity, and this one-to-one function is kind of really difficult. And for part C, for piecewise inverse function is not out, but it's quite rare. So I show you once how you did it. Okay, is how to consider the stuff piece by piece. Okay, so that's it. For the paper 2 is a bit more normal. There are some new type that they put emphasis on, but all of the questions seems to be quite normal, that we have seen them before and they're within the syllabus. So I would break them down if there is a chance. But first of all, before I do that, I'm gonna break down the SL paper, SL specimen paper as well on the new syllabus. Okay, so if you're doing SL, you can tell your friends go do SL on that. So that's it. Okay, I hope you would really use this holiday to prepare your IB, and so wish you luck.